Hello learners, this class is for B.Sc-IV Sem, second year 4th Sem, and the topic name is Fresnel's biprism. So, to produce an interference pattern, we are using this Fresnel's biprism experiment. So, Fresnel is a scientist who used a biprism. Okay, what is a biprism here? So, you can see two prisms are there. Okay, there are two prisms, that is known as a biprism, which consist of two prisms placed base to base. So these are placed like here, base to base. Okay. By proper grinding and by proper polishing the plain glass plate, this combination of two prisms are obtained. So how is the angle made with this biprism means the obtuse angle of the prism is about 179 degrees here. Okay, 179 degrees here, and 1 degree is half here and half here, right? You can also see the experimental arrangement or the diagram that is representing the Fresnel's biprism experiment. So here is our source. Okay, here is the Fresnel's biprism placed. Okay, the source, the light is illuminated here, and after going through the biprism, it's moving like this. See, this is another ray, it is moving like this. It is another ray here. After touching to the prism, it is moving like this. Okay, here this is the way it is going, and this one also, it is the way here it is going. Fine. Did you understand the rays that are coming and being illuminated on the prism and then moving ahead to form the pattern? Okay. So you can see, once again I'll show you, this is the illuminated light that is passing after touching the biprism. It is passing in this way. Here after touching, it is passing in this way. Okay, here after illuminating, it is passing in this way. Here it is passing in this way, and the straight line one is passing in the straight line only. Okay, this is the diagrammatic representation. Okay, now let's see the theory, what has been written. So the action of biprism is to produce two coherent images of a given slit which are separated at a certain distance and behaves as two coherent sources. Now, a monochromatic light source such as sodium vapor lamp is illuminated from the slit S. Okay, from the slit S, we are illuminating a sodium vapor lamp source. So here the sodium vapor lamp's light source, it acts as a light source, and we have to find out the wavelength. Okay, that is the wavelength that we have to determine. Now the biprism is placed in such a way that its refracting edges is parallel to the length of the slit. Okay, now you can see here in the diagram, the refracting edges are parallel to the sources. Okay, now the edge B, where is the edge B? So this is our edge B. Okay, the edge B divides the incident wavefront in two parts. Okay, now how the experiment is working? The experiment is of division of wavefront form. Okay, the experiment or the wave, the interference pattern that we can see is because of the division of the wavefront. We have already seen in earlier classes the interference patterns can be formed by two methods. One is by division of wavefront and another one is by division of amplitude. Okay, so this Fresnel's biprism experiment is the interference pattern we are getting in this Fresnel's biprism is due to the division of wavefront. Okay, so here at the edge B, the incident wavefront is divided into two parts. The top portion of the wavefront is refracted downwards, and it appears to have diverged from virtual source S1, and the lower portion of the wavefront is refracted upwards and it appears to have diverged from virtual source S2. So what it is saying, you see here, this is the edge B. Okay, from here the wavefront is divided. Now you can see the source is going like this, but after emanating, after touching the biprism, it goes downwards. Okay, it is refracted downwards, and here also like this, but it should go like this, no, but no, it is moving in this way. Okay, in this way. So a person who is seeing from here, okay, suppose this is an eyepiece, a person who is seeing from here will it appears, so this pattern appears as if the light is coming from somewhere from here. Okay, somewhere from here. So this is the S1, which is virtual source. Virtual means not really there. Okay, we are that is just assumption only. Okay, that appears to be coming out from the S1, but actually it is coming from S. Okay, the person or the eyepiece from which we are seeing, so it appears to come from this S1. In the same way, if the person who is seeing from here, he assumes that this light is coming from this S2, but it is not coming from S2. So this S2 is known as virtual. S1 and S2's sources are known as virtual sources. S1 and S2 are known as virtual sources. Actual source is S, but it appears as if they are coming from S1 and S2 if we are seeing from here and here. Okay, so S1 and S2 are said to be as virtual sources. Understood? No. Hence the light waves produce interference fringes. So after the light wave is coming and illuminating, then we can see the interference fringes, because there we can see two waves, no? Two waves. So the two waves are interfering and we can see the pattern. Okay. So interference fringes are formed in the overlapping regions EF, which is on the screen, placed at O. In the region EF, the interference fringes have equal width, but beyond E and F, fringes are of large width. We can observe the fringes by replacing screen by an eyepiece. Okay, if that is screen, we can see. If we can see by an eyepiece there. As a point O is equidistant from S1 and S2, the central bright fringes of maximum intensity is formed here. Where the maximum intensity is formed? At the point O. The point O is at equidistance from S1 also, and equidistance from same distance from S2 also. So we can see the central bright fringe. Central fringe is bright and it is of maximum intensity. And on either sides of this O, we can see like bright and dark fringes alternatively. Now I will show in the diagram. See, you can see the point O here with the maximum intensity over here. Maximum intensity at O, and alternate bright and dark fringes. Okay, these are alternate dark and bright fringes like this. Okay, so here the interference is happening due to the division of wavefront. Because of the division of wavefront at B, we can see the pattern here. This is a bright with maximum intensity. Okay, this is the interference pattern. This is a screen. From here we are seeing, so this is eyepiece. Okay, this is screen E and F. EF is a screen. Okay, ABC is the Fresnel's biprism. Biprism. This is the biprism. Okay, and this S1 and S2 are virtual sources which are not actually there. Actual source is S. Okay, and the distance between S and S2 is D. Okay, D, and the distance between the source and the screen is capital D. Okay, remember this. D, small d is the distance between S1 and S2. Capital D is the distance between screen and the sources. So So distance between two dark fringes or two bright fringes is beta. We have already seen this, the fringe width, okay, beta. Now beta can be found out by using micrometer. We have to use micrometer to find out the width of the fringes, the distance between the fringes. So capital D is a distance between source and the screen that can be measured easily by using the scale. But small d, that is a distance between two virtual sources S1 and S2. The distance between S1 and S2 is d. But it is not easy to find out small d. We cannot find out small d, or we cannot find out the source's distance. The distance between two sources cannot be found out by the scale, right? Because S1 and S2 are not actual sources. They are just the virtual sources. Then how can we find out with a scale or anything? So we have to use the other method here, which is known as lens displacement method. So to find out the distance d between S1 and S2, we are using this method, which is known as lens displacement method. Okay, to measure d, we use lens displacement method. Okay, after finding out the small d, we have to substitute in this equation. You see, lambda is equal to beta d by d. Beta can be found out, okay, by the micrometer, by seeing the fringes, distance between the fringes. Small d is found out by using the lens displacement method. Capital D will be found out by just using the scale. So by substituting beta, d and capital D at these places, we can find out the wavelength of the light. That is the experiment here. Now there is a question how to find out this small d. So this method you have already you are already aware of this method. So let's see here, this is S1 and this is S2. Let us suppose we are keeping the lens here. Okay, this is a virtual source. So you can see the S1 image here, S1 image here, and similarly you can see the S2 image here. Okay, let us suppose whose distance is some d1. Okay, here you can see the exact images, okay, correct images of S2 here and correct image of S1 here. Okay, so literally we can say this as d1. Now we can find out the distance and we can write d1 is equal to some 15 meters or 10 meters, whatever we get we can write. But to get the accurate d value, once again what we are doing, we are moving this lens which was here, no, now we are moving this lens at some other place. At some other place we are moving it, and then we are finding out the image of S2 where it is properly, correctly, exactly where we are getting the S2 image and where we are getting the S1 image. Then we have to find out the distance between that two places also, S2 and S1. Okay. So to measure d, a lens with focal length less than 1/4 of distance between biprism and eyepiece. So how much should be the focal length of the micrometer, or focal length of that lens? Focal length of the lens should be 1/4 less than the distance between the biprism and eyepiece. Biprism and eyepiece distance must be by 4 to the lens focal length. So the lens is adjusted at the position L1 till sharp image of S1, S2 are obtained in the first case. So we are getting D1, and in the other case also we are moving the lens to a certain distance to see the exact image, okay, sharp images, we are getting D2. So we have to get 2 Ds so that we get the accurate distance, accurate value. Okay. In this case the distance between slit and lens is objective distance U. Okay. So slit and lens, this is U, and lens and screen, this is V. Okay, and we got D1. After moving to certain distance, again we are getting the sharp distance, sharp images. So we have found out D2 also. We know U, we know V, we know D1, we know D2 now. So substituting the equations, M1 is equal to D1 by D, or M2 is equal to D2 by D, that is equal to V by U and U by V. Now we are writing d1 d2 by d2, multiplying these two equations. Multiplying these two equations, we get d1 d2 by d square is equal to vu by uv. Vv cancel, uu cancel. d1 d2 by d square is equal to 1, or we can write d square is equal to d1 d2, or we can write d is equal to under root of d1 d2. So now we got the value of d. So we have to put the d value in this equation of lambda. So we will get the lambda, the wavelength that is to be determined. We have to substitute in that equation, we will get the wavelength. As we know beta value, small d value and capital D value now. We also will get the lambda value. So this is the way how we are using Fresnel biprism to find out the wavelength of any light. Okay. Thank you.